This is section 4.5, exponential and logarithmic equations. Suppose you invest $3,000 at 2% annual interest compounded yearly. When will you double your money? Doubling our money, so that would be $6,000. When are we going to have $6,000, right? Starting with 3,000. This is a compound interest kind of problem. If we think about or remember our compound interest formula, we know that we always multiply the principal times 1 plus our interest rate as a decimal. And since this is compounded yearly, it's just going to be once here to the power of t. I divide by n. My n is 1 in this case. And n times t would be 1 times t. T is unknown because we're actually asked about when we'll double our money. This is t. And double our money would be $6,000. So I'm looking at an equation here, and we actually came across something like this once in a previous video. This was our motivation for actually coming up with this idea of logarithms. We needed some operation to undo having a variable up in an exponent. Now that we have logarithms, we should be able to solve exponential equations. Let's talk about some solution methods, and we'll come back to this example. Note that an exponential equation is just any equation in which the variable occurs up in the exponent. Let me show you how we might solve an exponential equation. 6 to the x equals 1 over 36. This is definitely an equation in which the variable occurs in the exponent. This one's actually kind of a simple case because I could write both sides with the same base 6. Notice that this is the same as 6 to the x equals, well, 6 to the negative 2 is 1 over 36. And if the base is the same, certainly I could just equate my exponents. So sometimes this is really simple, and I'm just looking at writing both sides with the same base. Similarly, I could solve this problem. Here they already both have the same base e. So if the base is already the same, I can just equate our exponents. A little more complicated here. This is a quadratic. If I get everything on one side equal to 0, x squared minus x minus 12 equals 0, and I think this guy factors, so we may have two solutions here. X minus 4, x plus 3. X is either 4 or negative 3. And you can check both of those. If I plug in 4 or plug in negative 3, these exponents will be equivalent. If we can write the equation with the same base, it's pretty slick. What if we can't? Well, this is where we're going to have to undo that exponent, doing the opposite operation by maybe taking a logarithm on both sides. That seems consistent with equation solving methods we know of so far. If we can add something on both sides of an equation, or subtract or multiply or divide to create an equivalent equation, maybe taking a logarithm on both sides could work for solving an exponential equation. I want to look at this example, 2 to the x equals 15. I actually want to show you a few different ways to solve this. First of all, note that it's a little different than the previous examples we've been looking at because I don't see a quick way to write 15 as an expression with base 2. So it's a little bit different. Let me think through a few different ways we could solve this. Well, one thing we could do is just write this in logarithmic form. In logarithmic form, this is, well, remember our logarithm is equal to our exponent. This is the base 2 logarithm of 15. And actually, this is now solved for x. I would say this is a solution. It's an exact solution. If I want to get a decimal approximation for it, I can plug it into my calculator, or I might use the change of base and a natural or common log. So I might do something like this and get a decimal approximation. The natural log of 15 divided by the natural log of 2 is about 3.907. And you can check if you take 2 to the power of 3.907. It seems, well, 2 to the 4th is 16, so it seems like something a little less than 4 would work. You could plug it in and check it. We've got an exact answer and a decimal approximation. So one way we could solve this is just by rewriting it in logarithmic form. Let me show you another way. A second option would be to take this logarithm on both sides, and when we take a logarithm, I want to think about what base to use. I have several choices for that also. I might try a base 2 because I know a base 2 logarithm and a base 2 exponential are inverses. If I were to take a logarithm on both sides with base 2, it might look like this. On my left-hand side, the base 2 logarithm and the base 2 exponential undo each other, so this is just x. And as you can see, this is the same answer that we got previously. We might use a change of base formula and get a decimal approximation, but again, it's about 3.907. One more option. I want to try taking a logarithm on both sides. I actually don't have to restrict myself to using the base 2 logarithm. Let me show you this. Since I want to get a decimal approximation answer for this also, I might go ahead and take a natural logarithm on both sides. Here's what that looks like. In this case, the logarithm and the base 2 exponential don't directly undo each other, but I do have an exponent rule that allows me to bring down this x as a part of a product. This is, according to one of my laws of logarithms, x times the natural log of 2 equals the natural log of 15. One more step will get x by itself. I'm going to divide out by the natural log of 2. Note that I can't just divide by 2. This is one number itself, the whole thing, natural log of 2. So I have to keep that together, don't separate those. But this is going to give me, again, that same result, the natural log of 15 over the natural log of 2, or about 3.907. I chose to do natural log. We previously did the base 2 logarithm, which makes sense also. I could also do a common logarithm if I wanted to use that. Using natural log or common log is nice because it immediately gives us an expression that we can plug into our calculator and we don't have to do change of base. So depending on your calculator, you may choose to do natural or common log. Let's look at another example. We're going to solve this. I've put some additional directions in here. I want to note that we want to give both an exact answer in terms of logarithms and then a decimal approximation of the answer. So I want to make sure we have both in place here. I'm not going to do this using all three methods. That was writing it in logarithmic form, using a base logarithm to undo the base exponential, a matching base, or using a common log or natural log so that we more directly get to an answer that we can approximate on our calculator. Those were the three options we looked at. I'm going to just pick a method here, but note that you could do any of those. I think what I'm going to do here is maybe I'll use a common log on both sides. So let's take the common log on both sides to undo this exponential. Using a common log, since these bases don't match, I'm going to bring down 2x plus 3 as a multiple of log 5. These parentheses are pretty important because it's the entire thing times log 5. Now I just want to work on getting x by itself, so I'm going to start peeling away some other things. Note, again, I can't just divide by 5 to undo that. It's not the number 5, it's the number log 5. So I'm going to undo that product by log 5 with division by log 5. This leaves me with 2x plus 3 equals log 94 over log 5. I'm going to subtract 3 and divide by 2 to get x by itself. So this is a bit of a chunky answer, but I can write an exact answer involving logarithms here. Subtract 3, and maybe I'll write this as division by 2 multiplication by 1/2. This is my exact answer. Let's also plug in and get a decimal approximation. When you do, you should get about negative 0.0885. This is again a decimal approximation. That's why I'm using these squiggly equal signs to indicate that I've approximated with a decimal and it's no longer an exact answer. You should be able to plug that back into the original equation for x, and when you evaluate this, get 94, so that would be one way to check your answer. Let's try this one. Again, I want to give an exact answer and a decimal approximation. This one's a little bit trickier because I have a little bit more going on. I don't have my exponential term isolated. It's multiplied by 2 and 1 is added to it. Thinking of using logarithms on this one, I think natural log is a good choice because I can plug it in my calculator and it will directly undo that base e. If I were to go in here and just take a logarithm, natural logarithm on both sides right away, notice I'd run into a little bit of trouble. I don't have a log rule that allows me to deal with a logarithm of a sum. I do have one for a logarithm of a product. We can separate it as a sum. But taking this logarithm actually doesn't help me get this exponent down because of all this other stuff going on in here. So here's what I'd recommend. In order to make this a little bit more straightforward, why don't we just isolate our exponential term first? Why don't we subtract this one and divide by 2? That's going to leave us with e to the 4x minus 2 equals, well, 86 minus 1 is 85, and then we'll divide by 2. Now I can do logarithms once I have my exponential expression isolated. Now let me do the natural logarithm on both sides. This is going to come down, or I can just think of these canceling out because they are inverse operations. They have the same base. This is just 4x minus 2 equals the natural log of 85 halves. Add 2, divide by 4. Here's my exact answer, and I can also get a decimal approximation. That's 1.437 or so. One thing just to warn you about, again, we want to think of these natural logarithm expressions as one whole number together. I can't separate 85 halves from the natural log in this instance. I also can't go in here and add 85 over 2 and 2 because it's not 85 over 2, it's the natural logarithm of 85 over 2. So I can't add that 2 or divide that 4 with just 85 halves. So get used to thinking of this logarithm of a number as an entire number itself that can't be separated. In order to do operations with that, well, we have logarithm laws we can rely on, but only using those laws can we combine things. Here's a summary of what we've been doing to solve these exponential equations. First, isolate the exponential equation on one side of the equation, the exponential expression on one side of the equation. Then take a logarithm on each side using the laws of logarithms to bring down the exponent. And more specifically, I would recommend a common log or a natural log, or possibly if your calculator takes inputs of logarithms of various bases, a matching base to the exponential that appears. Then solve for the variable. I think we're ready to return to this compound interest example. We had written down this equation to determine how long it takes to double our money in this context. Let's go ahead and solve this. When I go in here, I might think about using a logarithm to undo this base. I actually could take a logarithm on both sides, but it's going to get a little messy because I have a product here. I'll have to use a logarithm law to separate this into a sum of logarithms. I think we'll stick with what we just talked about and isolate our logarithmic or our exponential term first. So let me get 1.02 to the t equals 2. And then take logarithms. I'm getting this exponential piece totally by itself, no product, sum, anything in front of it. This is a little bit better. Now if I take natural log on both sides, again, I have a choice. I could do different logarithms. I like natural log, probably because it's one fewer letter to write. I can just write ln. This is t times the natural log of 1.02 equals the natural log of 2. And then to isolate t, this is a product, so I'm going to divide by the natural log of 1.02. Not just 1.02, but the entire number, natural log of 1.02. That gives me an exact answer, which isn't real meaningful in terms of how long it takes to double our money, so I definitely want an approximation here. The natural log of 2 divided by the natural log of 1.02 is just about 35. This is our time. Remember, in this formula, it's always in years. It's going to take 35 years to double our money when we invest $3,000 at 2% annual interest, compounded yearly. I've got some for you to try for participation points. Give both an exact answer in terms of logarithms and a decimal approximation of the answer. number one might be an exception. I don't think you need logarithms to solve that one, but for the others, both an exact answer as well as a decimal approximation. Just answer one of these for up to 2 participation points this week. Remember to post in the Homework 9 discussion. I've got one more exponential equation before we move on. This is called an exponential equation of quadratic type. You'll see it looks a little bit like a quadratic equation. I've got my something squared minus something minus a constant equal to 0. It reminds us a lot of ax squared plus bx plus c equals 0. So that's why we're calling this quadratic type. It's a little bit different and difficult to solve using logarithms because if I go in here and take a logarithm of this whole thing, I've got a logarithm of a difference, and I don't have a logarithm law to deal with a logarithm of a difference. So having this e in more than one place with different exponents, so I can't combine them, it's a little more complicated. Here's how I'd like to think about solving this one. If we for a moment let a be e to the x, well, this is a squared, e to the x squared. This is a minus 6 equals 0. And when I write it this way, it looks just like a quadratic equation. In fact, I could even factor this into a minus 3a plus 2 and get two answers for a, 3 and negative 2. Well, this seems kind of helpful. These are equivalent to a, but remember a was e to the x, so I'm really saying e to the x is 3 or e to the x is negative 2. These are two equations involving exponentials that I can solve pretty easily. So again, I replaced e to the x with an a, saw that it looked like something I could solve by factoring. Changed a back to e to the x, and I'm left with two equations to solve. This is just going to be, if I put this in logarithmic form, the natural log of 3 is x. Over here, well, I could put this in logarithmic form. In either form, we see that we really don't get another solution. E to the x can't be something negative. E to the x, if you remember, has a range of positive numbers, just like our natural log has a domain of positive numbers. So I'm not going to get a second solution from this. Looks like the natural log of 3 is our one and only solution. That's an exponential equation of quadratic type. Let's talk about logarithmic equations next. If we can solve an exponential equation using logarithms to undo the exponents, we should be able to just do the opposite, solve a logarithmic equation, or one in which a logarithm of the variable occurs, using exponents. So let's give it a try. Log of x equals 2,786. Well, let's see. With our exponential equations, we had a few different ways to go about it. An exponential equation we could solve just by converting to logarithmic form. If I convert this logarithmic equation to exponential form, well, let's see, it's a base 10 to the exponent 2,786 equals x. And actually, here's a solution. That's a huge number, but we've got a solution for x. So I could solve this just by writing it in exponential form, or why don't we undo logarithms by using exponents? If I grab log x equals 2,786, maybe I can apply a base 10 to an exponent of each of these sides. So it would look like 10 to the log x equals 10 to the 2,786. And here again, I'm using that relationship that exponentials and logarithms are inverses. This is just x equals 10 to the 2,786. Either way, same answer. Here are some guidelines for solving logarithmic equations. We'll see some where we want to isolate the logarithmic term, just like we would isolate an exponential term for an exponential equation. In isolating this logarithmic term, it could involve using some of our log laws in order to combine logarithmic terms, so we'll see some of that as well. Write it in exponential form or raise the base to each side of the equation, and then solve for the variable. Let's try this. Natural log of 5 minus x equals 18. I'm going to choose a base e exponential. If I apply the base e with both sides as exponents, well, base e and natural log cancel out. This is 5 minus x equals e to the 18th. That means 5 minus e to the 18th is x once I solve for x. This is an example where we would want to think about getting the logarithmic term isolated first. So again, I might think, oh, there's a base 8 logarithm. Why don't I just raise both sides to a base 8? So it'd look something like this, 8 to this side and 8 to this side. However, because I have a sum in here, I've got a product, I can't just cancel these out. I have to isolate our logarithmic term first. So let's do this instead. Subtract 6. And then divide out this 3. Now I've isolated my base 8 logarithm. 204 divided by 3 is actually 68. Now I can use a base 8 or write this in exponential form. If I apply a base 8 to both sides, let me just do it this way. 8 to the base 8 logarithm of 4x is 8 to the 68. Now my base 8 logarithm and my base 8 exponential are inverses, so they undo each other. That's 4x equals 8 to the 68. And then we can divide both sides by 4. So another really huge number, but 8 to the power of 68 divided by 4. Here's one that has a couple of logarithms. When we looked at an exponential function that had a couple of different exponential expressions, one thing that we did was look at quadratic form for an exponential equation. In this case with logarithms, I think probably the easiest thing we could do is just combine these two logarithms. They're the same base, and I have a log law that would allow me to change this sum into the logarithm of a product. So this is really log of x plus 2 times x minus 1. Now if I take both sides with a base 10, I've got just x plus 2 times x minus 1 equals 10 to the 1, or 10. This is going to be a quadratic equation. I think our best bet is to get everything multiplied out and on one side equal to 0, and then we can see if it factors, or so we could solve it that way. So this is x squared minus x plus 2x, so plus x minus 2. And if I bring 10 to the other side, this is x squared plus x minus 12 equals 0. And I think this factors. Plus 4 minus 3. This gives me two solutions for x. Let's just check these. I want to be a little bit careful here. I'm a little bit nervous because of this step. Note that if I took the log of a negative number here, the log of a negative number here, well, I can't evaluate the logarithm of a negative number. However, going from here to here, if I took their product, it would be positive. That means it's possible we got some extra solutions here that aren't really solutions to the original equation. Let's just check here. If I plug in negative 4, that's log of negative 4 plus 2 plus log of negative 4 minus 1. I think it happened here. Negative 4 plus 2 is a negative number. Negative 4 minus 1 is a negative number. Sure, when I multiply them and put them into this single logarithm, it works, but it doesn't work in our original equation. Negative 4 is not a solution. So something new to watch out for always. Check your answer. For domain issues, again, it happened because we used a log law here. 3 I think is okay. If we plug 3 in here, that's 5, that's positive, and that's 2, that's positive. So we should be fine in that case. Our only solution then is x equals 3. Let's try this again. I've got the base 5 logarithm of x plus 1 minus the base 5 logarithm of x minus 1 equals 2. I just want to emphasize this one more time. If I just did a base 5 to this entire quantity and a base 5 over here to this quantity, it's not really helping. I'm kind of stuck. I need this to be in a single logarithm first. It's tempting to say, oh, that means this is just x plus 1 minus x minus 1. It just cancels out these base 5s. but it doesn't because of this difference. That's not the way our exponent laws work. Instead, I need to combine these logarithms first. And I can do that using my log law that says a difference of logarithms is the logarithm of a quotient. So this is really x plus 1 over x minus 1. Now I can apply that base 5 on both sides to get x plus 1 over x minus 1. Since these are the same base, they undo each other, and 5 squared is 25. All right, so to complete this and solve for x, let me multiply both sides by x minus 1. That'll be 25x minus 25. I can subtract x and add that 25, and finally divide by 24. 13/12 is x. Just got one solution this time. Let's just double check. It's a positive number, but I want to make sure that when I plug it in, I don't have a negative result that I'm taking a logarithm of. Again, if this was a negative over a negative, it would become positive and be okay here, but not in our original equation. We need to check it in the original. 13/12 plus 1, that's certainly going to be positive. That shouldn't be a problem. 13/12 minus 1 is still 1/12, so that'll be positive as well. Go ahead and grab a calculator and plug this in and check the whole thing just to verify we get 2. In order to check if our answer has any domain issues, I'm basically just looking for whether when I plug it in, I get a negative input into a logarithm anywhere. Again, this is most likely to happen when we use one of our log laws to simplify before we solve a logarithmic equation. Got a couple questions for you. These are applications that should look kind of familiar, and I want to give you a chance to try these out for participation points. So if you haven't gotten any participation points yet in the homework 9 discussion, try either number 4 or number 5 for up to 2 points for a correct answer. One's about compound interest, and one we're given an equation for the amount of a radioactive substance remaining after T days, and asked a question that involves solving an exponential equation. Good luck, and let me know if you have any questions.